to have resonance, you have to have two different systems, and if they are in sync with each other, if they are at the same frequency or they have the same period, then one can cause the other one to resonate. So, regarde ça. Okay? You're not supposed to do that ever, but you know, there it is, right? Okay. It's like you get up on the ladder and it's like the ladder's not quite where you want it, so you can kind of walk the ladder. No. Okay. So here's this thing. It's got a frequency that it is wont, W-O-N-T, to vibrate at. That's its natural frequency. And that is, angularly, it's the square root of K over M. K is the springiness, M is the mass. The more springy it is, the faster it vibrates. The more mass it has, looking at that little formula, right, the slower it vibrates, correct? Does that make sense? Yes. And of course, you know, the more mass it's got, the more inertia it's got. That should make sense, right? This is a basic thing, right? So here I've got a fair amount of mass on there, and I'm going to add some force to it. So here I am. If you look, my fingers are moving up and down at some frequency, and that's having almost no effect on the mass, except that it is doing sort of an interesting thing there, sideways, yes? Are you seeing that? It's like, whoa. Okay. Now, if I slow it down, it gets closer and closer to that natural frequency. Slowing down. And when I match that natural frequency, watch what happens to the amplitude. It's like, holy cow, whoa, baby. Okay? Yeah. Basically, it's the amplitude's going to increase. When you match the frequency, it doesn't go to infinity. If it's undamped, if there's no way for it to lose energy, right, it'll go to infinity. Right? But real systems, of course, approach infinity. Basically, there's an equilibrium point where I'm pumping energy in at, say, 5 joules a second. It's got to lose 5 joules a second of, say, air friction in this case. Right? Okay? So then it will reach equilibrium. But it could be quite high. So that's what that graph is right there, is a system. And if you look, it shows the ratio of the two frequencies. Omega naught is the resonant frequency, and omega A is the applied frequency. Right? And there's some little formula there, but basically it just, the amplitude just goes crazy when you match the frequency of this, right? Now I'm going to put a different mass on here. This is less mass. This is half the mass, right? Do we all see that formula, omega is square root of K over M? So if I put half the mass on, how does that new frequency compare? It's going to be half the frequency or twice the frequency. Is it going to be faster or slower? Faster because it's less mass. It's easier to make less mass oscillate, right? So that's pretty basic, right? Okay. And this, by the way, carries through a lot of things. Yes. Look at guitar. The strings, they're all the same springiness. They're all tightened to about the same strength. So the strings that need to vibrate fast compared to the ones that vibrate slow, what are they changing? The mass, right? They don't change. They don't actually change the tightness. They're all about the same tightness, right? They've all got about 50 pounds of tension in them, which is why guitars need to be strong, right? 50 times 5 is 300 pounds of force, right, for heavy strings. Okay, so they all have the same springiness. It's the mass. How do you change the mass of a guitar string? Yeah, the diameter of them, right? The high strings are thin. The low ones actually have, they wrap brass around them to make them heavier. Okay, so here it is. Sure enough, that's faster, isn't it? Okay, is it twice as fast? Look at the formula. Is it going to be twice as fast? No, what is it going to be? Half the mass is going to make it, well, let's think about this. Isn't it square root of 2 times? Right? It's a square root, right? And so, and IB likes to ask these questions. They put this on a multiple choice, you know, and twice the mass, half the mass, right? They'll give twice the frequency, half the frequency. Square root of 2 times the frequency divided by the square root of 2, right? It's going to be faster, and it's going to be faster by a factor of the square root of 2, correct? Yeah? So it's going to be more, yeah. Say it again. You what? Assistance. Okay, hold on. But okay. So are we good? So this is the basic concept here. And if I drive this thing at a frequency that it will resonate at, it'll just go crazy. Okay. What's the question? All right. Now, let's do a better example. This is more fun. Here I've got a tuning fork, and this one plays this note, and this one here plays that note. Okay, they are the same note. They are tuned to each other, right? Now, the way this works is that the tuning fork makes the wood vibrate. The wood makes more air vibrate without the wood, these things, without the resonator boxes, these things would put out very little sound. Tuning forks in the air are just like, I can't hear that, okay? But if you hook them up to this, you can hear them. Or if you take, this is fun, take a tuning fork and stick it on the bridge of your violin, stick it on the bridge of your guitar, right? Or we could stick it on the banjo. It's like, wow, that's an amplifier, right? That's what they do. Now, this thing is going to make the air vibrate. The air is going to vibrate. This box is actually tuned to this frequency, and how you do that we'll learn later on. It has to do with standing waves and stuff, right? And then the air is going to vibrate, and then, well, anyway, let's just see. That's crazy, huh? We're transmitting energy across here. The sound is vibrating. That makes the air vibrate, which makes the box vibrate. This thing, since it's the same frequency exactly, it's tuned to it, right? Makes this vibrate. Isn't that cool? Yeah. Okay, now let's do an experiment. Let's have all you guys go, ah, as loud as you can. Just pick a random pitch and sing it, and I will do this. And let's see if we can keep that from resonating by putting too many frequencies at it. Are we ready? Make a loud noise right now. Ah! Now be quiet. Didn't work. It still did it. It picked that frequency out of all that racket, didn't it? Isn't that amazing? Yeah, resonance is beautiful for that. So imagine that you have every frequency of radio station broadcasting all at once. We do, correct? Okay. So on your radio receiver, there's a resonant electric circuit. Electricity can resonate too, right? Because electromagnetic waves are waves. They have a frequency, right? So you can make an antenna resonate at a particular frequency, and there's a circuit in the radio that you can tune to a particular frequency. So it resonates at that frequency. That's how your radio picks a particular frequency out of all of them. Isn't that cool? And it doesn't matter that the other ones are going on too. Resonance will pick out that one particular frequency. Isn't that neat? So when you have, does anybody have like high-powered, not like just like the little walkie-talkies, but you've got like, you're a ham radio operator, you've got things like that, yeah? Okay, they actually have quartz crystals in them that set the frequency of that, the resonant frequency, so it's exact, right? So when they talk about, that's one of the pieces of gear that they talk about like that. Okay, now I'm going to take this guy and I'm going to detune it. I'm going to add mass. What's going to happen to the frequency? It's going to be a lower frequency because it's got more mass and it's going to vibrate slower, correct? Let's listen. Is it lower? That is lower than... There we go. There we go. Those are called beat frequencies, right? Can I drive this one with this one now? No, he's tuned to the wrong frequency, yeah? That's yet another frequency. There we go, yeah. So it doesn't work, right? There we have it, right? Okay. Let's hit the right arrow. Okay. And then we could talk about damping. So let me get this guy going here. I got to put this one on there. Notice how I worked that noise from the hall in just seamlessly? I thought that was a good thing. Okay, I'm going to get this, let's get it going really good. Not too much though. This is how you destroy a rangefinder. I've had this thing. Okay, let's collect. How about erase and continue? Oh, we're going to have a better one than that. Okay, so there it is. This thing is actually lightly damped. So if we go back to our presentation, this is underdamped. Isn't what we're doing like incredibly underdamped? Yeah, it's only being slowed down by the air friction of moving that paper through the air. Yeah, and any internal friction that there might be in the spring itself, and that's it. So this is, if your car does this, you need better shock absorbers, don't you? So shock absorbers, really all they do is they absorb the energy that's put into the springs of the car. Right, that's the notion of, that's what they're supposed to do. So one of the things you can do with your car is stand on the bumper, right, and then jump off. And you can check the shocks. They should go over, beyond once, and then they should go right back to equilibrium and stop. If they go, and you know, many times, like our car when we were growing up, right, you're bouncing down the road, right? Okay, that's bad because eventually the car is going to start bouncing on the road, and then it's going to like not be touching the road all the time, which is, you know, on the face of it a bad thing, right? Okay, you know, there we have it. Now A is over damped. A is, instead of air, we would fill the room with honey. Imagine that, right? Okay, and we let the thing, we pull it down, and it's the fluid it's moving through has so much friction that it just slowly goes back to equilibrium. It would eventually get there, wouldn't it? Yeah. Might take a long time, 5 years or something like that, right? Okay, and then B is critically damped. So they actually have systems. Yeah, if you're an